Today I am going to discuss late code 1642, farthest building you can reach. We are given an integer array representing the heights of buildings, and we are also given some bricks and ladders. We start from the top of the building 0 and we move to the next building. To move from building I to building I plus 1, we have two conditions. So if the height of the current building is greater than or equal to the height of the next building, we don't require any ladder or bricks. If the current building height is less than the height of the next building, we can either use one ladder or difference of height, number of bricks. So we need to find out the farthest building we can reach using the given bricks and ladders. Let me explain the problem statement with an example. This is a given array representing the heights of the buildings, and number of ladders are 2. Let us see how the solution look like. Before that, let me write number of bricks required for each movement. So to move from building 0 to 1, we either require one ladder or 3 bricks. So to move from building 1 to 2, we either require 2 bricks or one ladder. To move from 2 to 3, we don't require any bricks or ladders because h of I is greater than h of I plus 1. So to move from building 3 to 4, we require 6 bricks or one ladder. To move from building 4 to 5, we require 4 bricks or one ladder. Let us see how the solution look like if we have one brick. So obviously we won't be able to, obviously we don't have 3 bricks, so definitely we need to use a ladder here for this moment. To move from building 1 to building 2, also we require 2 bricks, but we have only one brick. Here also we use one ladder. 2 to 3 easily we can move without any bricks or ladders. So for 3 to 4, we require 6 bricks, but we don't have 6 bricks. So we will be able to reach till the index 3. We started from index 0, so we will be able to reach index 3. So suppose if the number of bricks we have are 2, obviously we don't have 3 bricks here, so we use ladder here. Here the condition comes, we either use 2 bricks or one ladder. Suppose if you use the ladder, so to cover from 3 to 4, we require 6 bricks, but we don't have 6 bricks, and we also don't have any ladder since we used it to move from building 1 to 2. Suppose if you use 2 bricks, what we have to move from building 1 to 2, so we have one ladder. We can use that ladder to move from building 3 to 4. So we will be able to reach till the building 4. So this is the optimal solution. So we use 2 bricks for this moment and ladder for this moment. So we will be able to reach index 4. Let us see how the solution looks like if suppose we have 5 bricks. From above, you already might have come to the intuition. So for each index we reached, we are replacing the highest differences with ladders. So we replaced the 6 and 3 with the ladders, and we used the bricks to cover the remaining bricks, remaining differences. So Here we required 3 bricks. The difference is 3. So obviously we can cover this with ladder. For movement from building 1 to building 2, we require 2 bricks. This also, these two we can cover with ladders. Suppose we move from 3 to 4, obviously we can cover 2 to 3. So if you want to move from 3 to 4, we require 6 bricks. We replace these 3 and 4 with the ladders, and obviously we can reach these 2 uh, bricks with the given bricks. Because we have 5 bricks, we can easily cover these 2 bricks. So we will be able to reach index 4. To move to index 5 from index 4, we required 4 bricks. So let us see, we replace the top 2 with the ladders, and the remaining, how many bricks we required? 3 plus 2. Yeah, we already have 5. 3 plus 2 is 5. We already have the 5 bricks. So we will be able to reach till this index, that is index 5, that is building 5. So the naive approach is, whenever we encounter any new difference, we sort the differences list. Let us push this to list. So we sort this list and we replace the top L differences with ladders. So yeah, why you are sorting? To get the top L differences. So the complexity will be like n times we may need to push the differences. So and for each sorting we require n log n complexity. We require n log n complexity. It totally leads to n square log n complexity. To optimize this, we may think of basic data structure, that is min heap, just to remove this part, sorting every time to get top L differences. So we maintain a min heap of size L. That means whatever differences we have in this min heap are the top L till the index we covered. Okay, and yeah, let us iterate over the array for the same example. So we have the 5 bricks, so we keep 3. Since the size is less than the number of ladders, we again can keep 2 to the min heap. So to cover the next movement, we require 6 bricks. We keep the 6 to this min heap. So since it is exceeding the number of ladders we have, so we remove the top element. So min heap, it is the smallest element of the array. So we remove this and we cover this with the existing bricks. If we are not able to do so, that means we won't be able to reach index 4. So new min heap looks like this, 3 comma 6, and we already utilized the 2 bricks here, so we will be left with 2 bricks, 3 bricks. So to jump from, we already reached index 4. To reach index 5, we require 4 bricks. So we push 4 to this, and the size is L plus 1, size of the priority queue is L plus 1. So we need to remove the top element of the min heap, that is the root. That value is 3. 3 minus 3, yeah, we are able to cover these 3 bricks. So our final priority queue looks like 6 comma 4. That means these two differences we replace with the ladders. So whatever we popped out of this min heap, that is 2 and 3, that means these first two we cover these with bricks, and remaining two differences we cover with ladders. So if you see the time complexity for this, so we need to use the balanced min heap, so that every time we push any new element and when we pop the new element, so complexity remains in logarithmic. So to push the element and to pop the top element, the complexity is log of L, assuming that we need to maintain balanced min heap. So we also need to push n times. So total complexity will be n log L. It is much better than what we had earlier. I hope the solution is clear to you. Let me explain the code as well. Given the heights array, bricks, number of ladders. So integer the variable I represent is currently on which building we are present. We initialize one priority queue which internally implements balanced min heap in Java, equivalent of that. So we iterate over the heights. So we calculate the difference that we need to jump from building I to I plus 1. So if the difference is less than 0, we simply increment the I. That means we are moving to the next building. The difference is greater than 0, we need to ensure that we are really able to move to the next building. So we add the difference to the priority queue. So we are checking if the size of the priority queue is exceeding the number of ladders we have. So when this condition is executed, it always means the priority queue size is ladders plus 1, because we are doing it iteratively whenever we encounter the size greater than the ladders. So we obviously pop the top element. So we pop the top element to make the priority queue size as the number of ladders we have. So we remove that difference from the bricks we have. So finally, if the bricks is greater than or equal to 0, it is fine. If it's less than 0, we are unable to make this move. So we'll break it here. I hope the code also is clear to you. Thank you.